Chapter 2 is over chemical principles. Now, I know most of you guys are thinking, chemistry, this sucks. I really don't like chemistry. And I'm not good at chemistry. And I was once like you a long time ago. But as you're going to see, hopefully you'll see through the course of this class and your educational career, you'll see that chemistry is very important for biology. It's super important. Now, you don't need to know all the stuff that they're going to teach you in your actual chemistry class in order to understand life in its basic sense, but you need to understand some of it. So what I'm going to try and do here is I'm going to break this stuff down as simple as possible. We're going to start off very small and work our way to larger things. You'll start off with atoms, and then we'll work on bonds and different types of molecules. So hopefully this will not overwhelm you. This is, in many cases, a review of what you've heard in A&P 1 or Bio 1, depending upon your route to this course. So the first thing I want to ask you is, why do you think the biology classes always start off by studying chemistry? It's kind of strange that we're going into a different subject matter in the beginning of the class. And it really makes a lot of sense when you think about it. This cell right here that's pictured in this slide is a eukaryotic cell. You can tell because it has a bunch of organelles inside of there. And you can see it's really complex. Right? You have about 60 trillion of these things making up your body. Okay, and you're metabolizing all the time. So you think about your everyday environment. Room temperature versus body temperature. Normal body temperature is about 98.6. Right? And if you think about what you like your room temperature to be, it's usually somewhere in the 70s, usually around 72, 74 degrees, something like that. Okay, some people are really crazy and they like to keep their thermostat at 68, which wastes a lot of money, but they're nice and cold. But anyway, you look at these differences in temperatures, room temperature versus body temperature. Why are you warmer than room temperature? The reason why you're warmer is because your cells, your 60 trillion cells, are doing stuff all the time. They're doing things. They're carrying out chemistry. So you can think of your cells as tiny little chemical reactors, and you have 60 trillion of them doing all this stuff. So if there's a bunch of chemistry going on in each and every one of those cells, a cell is a fundamental unit of life. So there's a ton of chemistry involved in life. And so to understand life, you actually have to understand chemistry. Most of you guys are going to the healthcare field trying to make people better, right, if they are sick. And if you think about it, what are you going to do when they're sick? Most of the time, you're going to stick some chemicals into their body, right? Via IV, via pill form, you stick some chemicals in there to alter something that's going on inside of their body. So you're going to need to know some chemistry to get through. And to actually truly understand life, you're going to need to know a lot of chemistry. When I was at U of H doing my undergrad, it's amazing how much chemistry you have to take. You have to take Chem 1, Chem 2, thermochemistry, Organic 1, Organic 2, and physical chemistry. There's tons and tons of chemistry. So most bio majors are actually chemistry minors because of the amount of chemistry that you have to take. You also have to take biochemistry as well. So you look at the statement at the bottom here. It says all knowledge is connected. I actually saw that statement in a physics classroom a long time ago when I was teaching at North Harris. And it was just an epiphany. It just kind of clicked together. And this statement is really true. To understand life, in order to understand life, you need to know about chemistry, you need to know about physics, thermodynamics, you need to know about calculus. All these things, these laws that are out there, other sciences, actually will affect what's going on inside the cell, because the cell cannot violate all the different laws that are out there. Right? You can't violate the laws of thermodynamics. Energy is neither created nor destroyed. It just moves, switches around to different forms. So all these different areas of science and all these different subjects do affect what's going on here. You have to know about physics, because the laws of physics apply inside of the cell. And so you have these different areas of biology that are kind of like considered gray areas, like biochemistry, fusion between biology and chemistry, biophysics, fusion between biology and physics, and then even bioengineering. You know, look at what's going on inside the cell, look at the structures inside the cell, and apply them to different areas of science. And so these other areas are going to be very important in helping you understand life. Okay, so when we're talking about chemistry, this is as small as we're going to go here, the atom. We're going to talk about the different subatomic particles and their different characteristics. Okay, so if we look at the different subatomic particles, we're going to start off in the middle here. Okay, this is the nucleus of the atom, and it's got two different subatomic particles inside of it. It's got protons that are positively charged and neutrons that are neutral. And you can have multiple protons in there, just dependent upon the atom, but the net charge of the nucleus is positive because of all the protons that are there. The third subatomic particle, seen in this figure as the black spheres, the blackish gray spheres, those are the electrons. Electrons are attracted to the nucleus because they have a negative charge. So each one of these electrons is going to have a negative charge. And they are found outside of the nucleus in electron clouds. These electron clouds actually have very, very different shapes, dumbbell shapes, spherical shapes, stuff like that. They're not all circling around the nucleus in these nice, perfect circles. Okay, but we're not going to go into all that stuff. Okay, we're just gonna use this model here to help us understand the atom. So we have this positively charged nucleus. It's in the middle, these huge protons and neutrons, and this model here is not to scale because the electrons are actually very, very tiny. Okay, they're actually 1/2000th the size of a proton or a neutron, but they move around. In, if you think about this slide or this atom as having this a certain amount of space, okay, the space the atom takes up is like a huge yard. The electrons will roam around in this huge yard. Even though they're really, really tiny, they're going to move around huge areas around the atom. And actually, most of the space that's occupied by the atom is going to be where the electrons roam around, okay, in these different clouds around there. So for the most part in this class, we're going to leave the protons and neutrons alone. We're going to focus on the electrons, and you're going to see why in a second. These electrons are actually really, really important for biology. Is they have energy of motion, which is kinetic energy, because they're moving around, they're hauling butt actually around the nucleus of the atom. But more important biologically is they have potential energy, that's stored energy. And you're going to see the cell use this potential energy to actually do work. So you're going to release that potential energy, get this atom to do work. When it comes to atoms, a lot of them are uncharged, and that means that the number of positive charges equals the number of negative charges, so the number of protons equals the number of electrons. But that's not always the case. Sometimes an atom will have more protons than electrons, or vice versa, more electrons than protons. So if they have one more than the other, then what happens is they end up becoming charged atoms, and charged atoms are called ions. So we're going to see some ions a little bit later in this presentation. As I said before, when it comes to these atoms, we're going to basically leave the protons and neutrons alone. We're going to focus on the electrons. And the reason why is because when two atoms come together, okay, if you look at these two atoms here, the sodium and chlorine, if you look at these pictures, you can see once again the electrons are in energy levels or energy shells. They have a certain amount of potential energy. And when you look at these two atoms, okay, the electrons are the golden spheres. The nucleus is actually a silver sphere in the middle. As these two atoms move closer and closer together, think about which subatomic particles are going to interact with one another first. It's going to be the electrons because they're outside. Okay, they're in the outermost part of the atom. So we're just going to basically focus on the electrons, and we're not going to focus on all the electrons. We're just going to focus on the electrons that are in the outermost energy level. Those are called valence electrons. You can think of them as action electrons because things are going to happen to these valence electrons. They'll be stolen, taken away, given up, they'll be shared, and they'll form different types of bonds because of these actions of these valence electrons. Now, these atoms are floating around in space, different spaces all over the place, and they're going to, as long as their outermost energy level is not full, they're going to interact with one another. Because they're not considered happy until, we'll just say happy for them to make it nice and simple. They're not going to be happy until their outermost energy level is full, and that's called the octet rule. So until their outermost energy level is full, they're going to start interacting with other things that are around them. So they'll take some electrons, they'll give up some electrons, they'll share some electrons to satisfy that octet rule. And when they do that, they're going to form bonds, different types of chemical bonds. Now what bonds do is they hold atoms together in a stable association. And there are three major types of bonds. There are ionic bonds, covalent bonds, and hydrogen bonds. And I've highlighted certain parts of these words for these terms to help you remember what's going on. Ionic bonds involve ions. A short while ago I told you what an ion was. It's a charged atom. So you have two different charged atoms coming together and sticking together because opposite charges attract. I'll show you how that forms in a second. The second type of bond there is a covalent bond. That prefix co means with or sharing, and we're going to see how that plays into the formation of a covalent bond. And then lastly, we have the hydrogen bond. There's actually one more type of bond we'll talk about in this lecture, or actually the next part of this lecture, but these are the three we're going to talk about initially. So the hydrogen bond, you can think of them as gangsters. And I'll explain in the end why you can think of them as gangsters. So they really do behave like gangsters. It's one of the analogies that one of my students came up with, and it actually really makes sense. So why are there three different types of bonds? Okay, there are three different types of bonds because atoms have different properties. And when they have these different characteristics, they're going to behave according to their characteristics. And one of those characteristics that atoms have to deal with is a property called electronegativity. It's an affinity for electrons. It's kind of like how greedy they are for electrons. Some of them are really, really strong. They're really, really greedy. They have their electrons. They're going to hang on to them. They want more of these electrons. And those types of elements are going to be up here on this side of the periodic table. They're very, very strong. Okay. On the flip side, you have those that have a low level of electronegativity. Very, very little electronegativity. They can barely hang on to the electrons that they have, and they'll readily get rid of them because they're so weak. Those elements are going to be on this side of the periodic table. Okay. So we have this trend in this periodic table, and there's actually a lot of information that you can get from this periodic table besides the trend in electronegativity. The strength of electronegativity, as you move from this direction to this direction, it gets, these elements get stronger and stronger. Okay. Now there is one exception to this trend, and that is hydrogen right here. It should actually be sitting right on top of carbon because they have the same exact strength as noted down here. That's one exception to the rule. You need to memorize that exception to that rule. Okay, so that's just one of the trends that you can get from the periodic table. Another thing you can learn from the periodic table is the number of valence electrons. Anything in this first column here has one valence electron. Anything in the second column has two. We're going to skip 3 through 12 because those are funky transition metals. We don't want to deal with them. We're not going to deal with them in class. Anything in 13 has 3. Anything in 14 has 4. 15 has 5. 16, 6. 17, 7. And then the 18th column over there has 8 valence electrons that are over there. So that's some more information you can get from the periodic table. So when you're looking at the types of bonds that are formed, you have to look at the differences in electronegativities of those atoms that are taking part in the bond. So what's going to happen is we're going to see in a second, we'll look at ionic bonds. In ionic bonds, there's a huge difference in electronegativities. In covalent bonds, there's very little difference in electronegativities, and sometimes their strengths are exactly the same. And those are the two major types of bonds. Hydrogen bonds are a little bit different than those two. But when you're looking at what type of bond is going to form, and I'm not going to ask you this on a test, I just want to explain what's actually going on and why we have these different types of bonds. In ionic bonds, you'll see usually something like when we talk about the formation of table salt. Sodium is right here. It's very, very weak. Chlorine is over here. It's very, very strong. There's a huge difference in electronegativities. Okay, so we'll have some stealing going on whenever it comes to the formation of table salt. You're going to see, and when electrons are stolen, what that means is something that was uncharged is now going to be charged. So it's going to form an ion, and that's why we call them ionic bonds. In other cases, what we'll see is bond between carbon and hydrogen. Remember, carbon and hydrogen have the same exact strength. They have the same exact strength, and they can't steal. So what do? They share. You'll also see when some of these elements are really, really close on the periodic table, like carbon, nitrogen, and oxygen, even though they have slight differences in their strengths. The oxygen is stronger than the carbon, nitrogen is stronger than the carbon. They're still not strong enough to steal, so what they do is they share. Okay, so the first type of bond we're going to talk about, the ionic bonds. Now, ionic bonds involve ions. These are charged atoms. That means that there are different numbers of protons versus electrons. And usually, to make this happen, what happens is electrons are lost or gained. Okay, and once again, this has to do with the differences in strength or electronegativities of these different atoms. So, as I said before, we're going to look at the formation of sodium chloride, which is table salt. So, our first atom is an atom of sodium. And if we look at this atom of sodium, we can see that the electrons are in their energy levels, and it has a single valence electron. If we look at this periodic table up at the top, the sodium is over here. Okay, that means it is very weak. Very, very hard to draw on the screen. Okay, so it's very, very weak. Okay. Over here we see chlorine. Chlorine actually has 7 valence electrons. So outlined right here. And chlorine is over here on the periodic table. It's very, very strong. So we have a huge difference between electronegativities in these two things. Chlorine is very, very strong. Sodium is very, very weak. Okay. Chlorine will keep its electrons, and it has plenty of strength to try and get more. It depends upon who it's trying to get them from. If it's getting them from somebody that's very, very weak, that weak atom will actually barely be able to hang on to its electron and actually will readily give it up to somebody who's super strong. So when the sodium comes close to the chlorine, what's going to happen is chlorine's basically just going to steal that electron away, and that's what's shown here. Okay. Sodium comes close to the chlorine is going to steal that electron away. Now it has 8 valence electrons, and it's happy, it's satisfied the octet rule. Okay. But it has 1 more electron than protons, so that's why it's got a negative charge. Okay, and it's an ion. We call that type of ion that's negatively charged an anion. The sodium had 3 energy levels, but it gave up that last electron in the outermost energy level. Okay, so it lost that outermost energy level, and if you look at it, its outermost energy level now is full. It has 8 valence electrons, but now it has 1 more proton than electrons. So that's why it's positively charged. Okay, and that's a cation. Okay. So the chlorine atom stole away an electron from the sodium, picked up that extra electron, became negatively charged because now it has more electrons than protons, became an anion. The sodium gave up that electron, has more protons than electrons, becomes positively charged. That's not where this interaction ends. What's going to happen is you have a positive next to a negative, and since you have opposite charges, they are going to stick together, and they are going to stay stuck together because of the opposite charges. Now, I want you to realize that something else was transferred, not just charge. Besides charge, there's also potential energy. These electrons contain not just negative charge, but they contain potential energy. So whenever this reaction occurred, sodium actually gave up some of its energy, potential energy, in that electron to the chlorine atom whenever that it formed the chloride ion. And so that chlorine atom, when it picked up the extra electron, it gained some energy. And that sodium ion lost some energy. So energy was transferred in this reaction from one atom to another. And we're actually going to see a lot of that in chapter 5. So that's how ionic bonds form. Okay, one atom gives up an electron, the other one actually takes it away from the weaker one, and you get this charge-based attraction because of the ions that are formed. And covalent bonds, what actually happens is, excuse me, you have 2 atoms coming together, and they are very, very similar in electronegativities. Classic example of this is the formation of a hydrogen molecule. You have 2 hydrogen atoms coming together. Now with a hydrogen atom, it only has 1 energy level. And remember that according to the octet rule, they will start interacting with one another until their outermost energy level is full. And if we look at the energy levels, since they only have a single energy level, that first energy level can hold a maximum of 2 electrons. So with these hydrogen atoms, all they need is 1 more electron to satisfy the octet rule. Okay, remember, just because of that first energy level is an exception to the rule. It can only fit 2 electrons. So each one of these is looking for another electron. They come into contact with one another, and since they have the same exact strength, what's going to happen is these hydrogen atoms will actually end up sharing that electron. These electrons will spend part of their time around this nucleus, part of their time around this nucleus over here. So they'll spend, in this case right here, they actually have the same strength, and so this will be half the amount of time around here, half the amount of time around here. There's 50-50 sharing of these nucleotides. We're just spending half the time around there. Okay. Now when it comes to these molecules, okay, there's different ways that we can talk about these molecules, okay, or we can share information about these molecules. One of the ways is through a structural formula. And we indicate a covalent bond, which is a sharing of the electrons, by this line that's right in the middle, just a straight line that's between these 2 atoms. Okay, it shows who's connected to who in a structural formula. Okay, that's the value of the structural formula. And some of these are going to get really, really complex. Okay, in a molecular formula, it tells you which atoms or elements are part of the molecule. And the structural formula will give you the shape of the molecule. So if we look down here, we've got some covalent bonds that are forming the water molecule. A shorthand way of drawing that water molecule is like this. So here's a covalent bond here, here's a covalent bond there, and each of these lines right here indicates that these atoms are sharing a pair of electrons. We're going to see that carbon is very, very important. It forms covalent bonds with a lot of different things. It's very, very important for life. Carbon has a valence of 4, which means that in order to satisfy the octet rule, it has to share with some other atoms, right? And so it's going to need to form 4 other bonds. And we can see in this first image here that carbon can actually form 4 covalent bonds with hydrogen. Carbon can actually not just bond to hydrogen, it can bind to other things. And here we see a carbon bound to another carbon, so we have this 2 carbons with 6 hydrogens around it. So each one of these single lines is a single covalent bond. Carbon doesn't just have to share 1 pair of electrons with something else. It can actually share 2 pairs of electrons and form what's called a double covalent bond, which is shown here. Indicate double covalent bonds with 2 lines. So between those 2 carbons, there are 2 pairs of electrons being shared. Carbon can actually even share 3 pairs of electrons, and forming a triple covalent bond, which is shown here in this image. The carbon is actually one of those atoms that can do a variety of different things. Because it can bind to 4 different things, there are a variety of different shapes that it can form. So you can see down in this area here some of the different things or shapes that can be formed. And what's really, really important for molecules is their shape. Shape and charge determine the function of these different molecules. So you can see that these carbons can form branch chains, they can form ring-like structures, even squares. There's a variety of different shapes that can be made. So you can think of carbon as like a building block, because we are carbon-based life forms. It's kind of like with this connect set over here. You can actually make a variety of different things. In this case, they're making what looks like a Ferris wheel, but you can form a variety of different things with all these different building blocks that are there, and that's what is happening in life. We have a bunch of different molecules that have these huge what we call carbon skeletons, and they're going to have different shapes, which are going to give them different functions. Now you can see that some of these items or some of these molecules here are actually labeled. I'm not going to ask you to identify different molecules on the test. I'm not going to draw something out and say, what is this? I'm not going to do that because this is not chemistry class. I just wanted to show you the diversity that's out there. So these carbon molecules form a variety of different shapes, and that's going to enable, one of the things that's going to enable life to exist and all the different complex processes to go on inside the cell. Now, as I said, when it comes to types of covalent bonds, we've got a bunch of different types of covalent bonds. Depending upon the number of electrons shared, you can have a triple covalent bond, a double, and a single. Triple covalent bond is sharing 3 pairs, double 2 pairs, a single is 1 pair of electrons. Now when it comes to these covalent bonds, just because they're sharing electrons doesn't mean they have to share it equally. Sometimes they are sharing it equally, sometimes they're not sharing it equally. It depends upon their electronegativities. Okay, now in a covalent bond, the electronegativities are going to be similar or the same. Okay, but just because they share those electrons, as I said, it doesn't mean they have to share them equally. Sometimes the 60-40, 70-30 just depends upon their differences in strength. They're not really strong enough to steal electrons, but they may take them a little bit more often than not. So if there's equal sharing going on between the atoms that are taking part in a covalent bond, then that's called a nonpolar covalent bond. If there's unequal sharing, if there's one atom that's taking part in that bond that's stronger than the other, there's going to be unequal sharing, and that's going to be a polar covalent bond. When we look at these covalent bonds, you're going to see a bunch of different types. It's going to be important that you know the difference between a nonpolar and a polar covalent bond, especially when it comes to interaction with water. But it's also important to know that these covalent bonds hold energy. They hold potential energy. Because they have electrons inside of them, they're going to hold potential energy. So when the cell makes a covalent bond, the cell is going to store energy in that bond. If a cell breaks a covalent bond, energy is going to be released. And we're going to see that happening inside of the cell to move energy around from one place to another. Bonds are going to be broken, bonds are going to be formed to move energy around, especially in chapter 5, to actually eventually move it into the universal energy currency, move that energy into the universal energy currency, which is ATP. And that's what we're going to look at chapter 5. In chapter 5, we're going to see the production of ATP by moving energy around, by making or breaking bonds. So when we look at these covalent bonds, okay, it's important that you understand what types of bonds are polar, which types are nonpolar, especially when interacting with water. So I've put this little diagram here to help you figure out what's going on. When you look at a molecule, what you want to do is you want to look at the different atoms that are taking part in that molecule or playing a role in that formation of that molecule, and you ask yourself, is one of these stronger than the other? Is it yes or no? If they both have, if all the molecules, if you're looking at just a single bond, if both of those atoms have the same strength, okay, then one is not stronger than the other. They will equally share those electrons that are part of that covalent bond, and that's called a nonpolar covalent bond. So a great example of this is this molecule right here that has carbon and hydrogen. It has 4 hydrogens there. So if we look at one of these bonds at a time between this carbon and this hydrogen, looking at that bond there, you have carbon and hydrogen, which in our electronegativity trend here, you know that there's an exception, and the exception to the general trend is that carbon has the same strength as hydrogen, or hydrogen has the same strength as carbon, so they have equal strength. That means that one is not stronger than the other. We'll go to the no side. So that means that this bond right here is a nonpolar covalent bond. Why? Because these two atoms have the same strength, which means there's going to be equal sharing of that bond, of those electrons that are in that bond. If we look on the other side, over here, we see a water molecule. Oxygen's here on the periodic table. Hydrogen has the same strength as carbon, so it's over here. So who's stronger? Oxygen is stronger. And that means hydrogen is weaker. So when we look at this bond right here on this side, we see oxygen is stronger, hydrogen is weaker. When you have one stronger than the other, your answer is yes. That means it's a polar covalent bond. And if we look at this bond here, the stronger is going to have the electrons more of the time. So that means if the electrons are going to be around the nucleus of the oxygen more of the time, they're going to bring their negative charge there a little bit more than around the hydrogen, which means that oxygen is going to have a partial negative charge. The electrons are going to be around the hydrogen a little bit less than the oxygen, so this is not going to be as negative, so that means it's partially positive. And so if we look at this bond right here, it has poles. There's a negative pole here, and there's a positive pole here, kind of like a battery. So that's why we call it a polar covalent bond. The same thing can be said about the other side here. Oxygen is stronger, hydrogen is weaker. The stronger is going to keep the electrons more, so it has a partial negative charge. We indicate partial charges with those parentheses. The hydrogen is not going to have the electrons so much, so it's going to have a partial positive charge. This is a polar covalent bond as well because of the unequal sharing of those electrons. And when it comes to relative strengths, nonpolar are actually stronger than polar covalent bonds. You think about teamwork. Equal sharing of the work makes a stronger team. Unequal sharing makes a weaker team. And you know you've been in group projects before where you have unequal sharing, and a lot of times those groups don't work out. They disintegrate in the end, and it really, really sucks. People can't work together. All right, now our last type of bond that we're going to talk about in this presentation is the hydrogen bond. These bonds are going to be due to partial charges. So remember when we look at this water molecule here, oxygen is stronger, hydrogen is weaker. And because of these differences in strengths, you have partial charges, you have partial negatives. A partial negative around that oxygen, and they're actually going to have two partial negatives because you have two different covalent bonds, and then you have partial positives here. So these are partial charges. And if we look at water in liquid form, it's actually going to associate with other water molecules via these hydrogen bonds. And these water molecules are going to change their orientation based upon what partial charge they're around. So if we look at this figure over here, when water is in the form of ice, it actually forms 4 hydrogen bonds with other water molecules. So you can see this central water molecule actually has partial negative area, partial positive areas. And when dealing with this partial positive hydrogen that's right here, you can see that this other water molecule has oriented itself so that the partial negative section is next to that partial positive. Okay. And so there's going to be a weak force of attraction. These aren't full charges, these are partial charges. So there's going to be this weak force of attraction, which is called a hydrogen bond. And we indicate hydrogen bonds by drawing dotted or dashed lines, showing that they are weak, very, very weak interactions. Okay. If we look on the other side, with this other hydrogen that's here, you can see this other oxygen, which is partially negative, is going to associate with the partially positive that's here, forming another hydrogen bond here. When dealing with the oxygen, which is partially negative, you can see how these other water molecules are actually changing their orientation, such as the partially positives are next to this partially negative. So you form a hydrogen bond here. And with this water molecule, that partially positive will be weakly attracted to the partially negative there. So you form another hydrogen bond. So there are a total of 4 hydrogen bonds that can be formed when water is in the form of ice. When it's in the liquid form, it forms about 3.5 hydrogen bonds on average. Okay, and then it's in gaseous form, the water has broken all those hydrogen bonds, and the water molecule is all by itself. Those are the different forms of water and how many different hydrogen bonds they have. In the form of ice, it has 4, liquid about 3.5 hydrogen bonds. And what that means is that this water molecule is here has enough energy to break one of these hydrogen bonds half the time. Okay, and then when it's formed the gas, then this has broken all of these hydrogen bonds and it just floats away all by itself. Okay. Now, besides being very weak, hydrogen bonds also have another characteristic. They are, even though they're weak by themselves, they're actually strong in numbers. So if you have a lot of hydrogen bonds, it can be very, very strong. A great example of this is when you do a belly flop. It hurts a lot. Okay, and you'll actually have some damage to your body. Your chest will get all red, your legs, sometimes your face will get all red when you hit that water. Okay, why does it hurt so much to do a belly flop? Because in order to penetrate that water, what you have to do is you have to break hydrogen bonds. Okay. And you're going to have to break trillions and trillions of hydrogen bonds for your big body to go into that water. Now you can jump off the low diving board, do a belly flop, and it's going to hurt, but it's not going to hurt as bad as if you go from a higher up position. And if you look at some of the people in the Navy, when they get on those aircraft carriers, those big old ships and stuff like that, they actually teach them how to jump off those ships the right way so that they don't die, because if they're jumping off a really high area and if they jump off and they land wrong, what will happen is it'll actually just feel like they're hitting concrete solid, because they would have to break so many hydrogen bonds to penetrate the water. It's gonna be one of those things where their body's gonna give out before all those hydrogen bonds break. So their body will break before most of those hydrogen bonds break. So it can be a deadly situation. So the hydrogen bonds are weak by themselves, strong in numbers, and that's why my student came up with one of my former students came up with the analogy of gangsters, because they're pretty much the same way. You can deal with one gangster, no problem. But once you deal with them and you have your issues with them, they're going to walk away. And you need to get the heck out of there. Because what they're going to do is they're going to go get their buddies, come back, and beat the crap out of you. You're still there. They're weak. So hydrogen bonds are pretty much the same as gangsters. They're weak by themselves, but strong in numbers. And we'll be seeing a lot of these hydrogen bonds, especially when we start talking about proteins and nucleic acids. You can see that the fact that they're weak by themselves but strong in numbers can be very, very important for those molecules.